Hello, this video is going to go over the best modeling perspective when it comes to putting together a multiple linear regression. A quick disclaimer is that there's not one way of putting together your linear regression model, especially when it is multiple linear regression model, where you have a lot of independent variables that you're going to be using to explain your dependent variable. For that reason, I can't say that this is the best one, but I think I find this the very straightforward way and very intuitive way. So that's why I'm going to talk about it in this video, and hopefully you can take this perspective and utilize it. In the next video, I'm going to show you a little bit more automized way of putting your multiple linear regression together. Before I show you the modeling approach, I should talk about correlation metrics and multicollinearity. I'm going to explain what multicollinearity is, but we already saw correlation, right? Correlation indicates a relationship between two different pairs of independent variables in linear regression. Is it good or bad? Is it good that our independent variables explaining each other? Like, for example, if they have a correlation coefficient of 0.7 or higher than 0.7 in the positive side, or less than negative 0.7, we usually claim that there is a strong correlation between those two pairs, right? Well, when it is the case, how should we approach this multiple linear regression? If you have two independent variables that are explaining each other, at least showing the relations, showing that there is a strong relationship between each other, should we include them in our multiple linear regression? Why this is a concern? This is a concern because it might mess up your regression equation. So it might give you a straightforward relationship in a different way. It might inflate the p-values, and you all of a sudden would decline having an important independent variable in your multiple linear equation. This might lead to several important consequences, and I think you should be aware of this issue. Well, how do we target this? We actually look at correlation metrics, but we don't really do much with the correlation metrics. Obviously, if there is a strong correlation between two pairs, where it indicates like 0.9 or just 1, maybe closer to 1, we tend to remove one of those variables before we even start doing multiple linear regression. However, multicollinearity is a much better indicator that shows strong relationship existing between two independent variables. And we do look at variance inflation factors to check this. And we do this after we ran our regression model. So all of a sudden, we can't just start calculating variance inflation factors. We have to run the regression analysis first, and we conclude that this is a solid one that we should go by. And then as a last check, I would run multicollinearity analysis and calculate VF values and decide whether I should do further moves on my regression. So what is multicollinearity? Multicollinearity is the term when we use that when two or more independent variables contain high level of same information. It's just a very similar term that we used before, correlation, right? So it is very similar, but multicollinearity can be measured by actually predicting one of the independent variables by using other independent variables to see how much explanation we can make on that specific independent variable. I don't want you to get confused. I don't really need you to understand the formula behind this. But there is a math somewhere here that I was actually going to show you how it can be found. This is the VIF value. That's a good indication of a multicollinearity. So if this VIF value, I have seen some implementation. If it is around 1, we can conclude that there is no multicollinearity. And if it is, some of the books suggest that it should be less than 5, but I have seen implementations where researchers have taken this to be less than 10, okay? So this is more like a relaxed assumption, but I would go by 10 because you don't really want to lose that much information in your multiple linear regression by dropping independent variables all of a sudden. So in this class, for the sake of simplicity, we are going to see if there's any multicollinearity or not by looking at the VF value. And if that VF value is greater than 10, we are going to actually drop that independent variable from the equation, okay? All right, so giving these all background information, so what would be the best way, and this is not the only way, to put together a multiple linear regression? Well, it is simple. I would start with including all independent variables into my equation, not removing them at all, and running a multiple linear regression and checking to see if the regression has a significance, right? So we check the p-value for the regression and we say that, if we reject the null hypothesis, that's good because it basically tells us that there's at least one independent variable that explains the change in the dependent variable. Well, if that's a check, then we look at the individual p-values, right? We look at the individual p-value and we see whether it is above our level of significance. Usually it is 0.05, but it might change depending on the application. If there are more than one independent variables exceeding 0.05 with the p-value, right? We select the one that has the largest p-value and we drop that from that regression line, a regression equation, and we rerun the regression without that specific individual independent variable. We do not drop all the independent variables, whose p-values are larger than the level of significance. We do this one at a time because we don't want to lose information. We run the test again, and then we look at the regression, significance of regression. We give it a check, then we look at the individual p-values again. If all the p-values are less than 0.05 or the level of significance that you decided, then we can keep that multiple linear regression in our use. If you still have large p-values, then you drop them one at a time. Drop those independent variables one at a time, whose p-values are larger than the level of significance. Okay, well, how do we check our model has improved or not? If you look at the R-square value, so whatever you add into your regression, right? For example, you added one more independent variable instead of dropping one, your R-square value is always going to go up. Okay, there's no question about it. If it is not going to go up, it's going to stay the same, but it's never going to go down. So therefore, we use adjusted R-square value to measure whether the quality of regression improved, right? Adjusted R-square value is going to be a better indication when you add a specific independent variable into the linear regression equation, okay? R-square value is, again, the interpretation is, it is the percentage of the variation in the dependent variable that can be explained by the independent variables. Adjusted R-square value has a very similar interpretation to it, but it also takes into account whether your multiple linear regression has improved or not. Of course, if you drop variables from your multiple linear regression, then this adjusted R-square value is also going to go down. But if it is not really going down significantly, then it's a good sign because you are getting rid of some noises in that data, and you're getting a much leaner, I would say, much simpler regression line, still with the high percentage of explanation on the dependent variable. Okay, so we continue this process. We start with all independent variables. This is called backward multiple linear regression, and there's a forward way to it. But I think backward is much simpler. You can look it up in your textbook or online to see what it means. And then we continue this, removing variables with high p-values one at a time until all variables have p-values with less than the level of significance. And then we do have one last check. We do have to check this multicollinearity issue. As I said, it might create so much problems. And we do call VIF function. It is very easy in R. It's just one line of code, and to see if the VIF values of these independent variables are all less than 10. If that's the case, we don't touch the multiple linear regression that we found in these 4 steps. If there is one or more of VIF values or independent variables with large VIF values that's larger than 10, again, we drop one at a time. Okay, we select the highest VF value, we select the independent variable with the highest VF value, and we drop it from the multilinear equation, linear regression equation. We rerun it, and we look at the p-values again, and we look at the multicollinearity again, and we conclude whether that should be the one that we should use. Okay. Okay. So let's see an example to highlight this procedure that I just mentioned. Let's see whether we can stick to this analysis. To do that, we do have a new data set. It's called banking Excel file. And I'm going to be working in a moment on R, but let me introduce the data to you. So in this banking data file, our bank is trying to investigate where to locate new offices, right? And then they do have this kind of, age information in that neighborhood, education level. I think this is years of education, average years of education in that neighborhood or district. And income level, average income level of that neighborhood, home value of that neighborhood. I think this is a mean home value. And then the average wealth of people living in this neighborhood. And they are trying to decide how much balance the customers would keep in their accounts, right? So if the balance is more, the bank is going to be utilizing that money more. So they're trying to decide where to locate their branch offices based on this data. So you immediately realize that there might be some independent variables here that are correlated, right? This income, wealth, and maybe this home value, they might be correlated because they are all representing literally the wealth of a family or person living in that neighborhood, right? So let's try to see whether we can actually use all these A, B, C, D, E column as independent variables, right? And then try to see whether we can predict the balance column. All right, let's go to R. So you do, let me clean this. Okay, so let's go to import our banking data set. It's an Excel file, so I select this. Here, my module 3, chapter 11, banking. Okay, I imported it. I do have my columns right, looking nice. It's already named as banking. Make sure that it is named banking. Let's go here and let's do, as we always do, pairs.panels, and then let's call this banking data frame, right? And then we would like to run the regression, we would like to run the correlation analysis between age, education, income, wealth, balance, without including balance, because balance is going to be our dependent variable. Of course, these are all going to be related to balance. So let's see if there is any, if there's any correlation between the independent variables, okay? So it's going to be age, column 1, column 2, column 3, column 4, and column 5. I put 4 here, but it should be 5. So it is basically telling me that go look for the correlation between the first 5 columns of this data frame. Let's first load library psych, right? We already installed it earlier. If you haven't installed this, go ahead, make sure that you install a psych, otherwise this wouldn't run. In my case, it ran already. So let's execute this command as well. Well, let's try to zoom in. Let's see what this is telling us. So do you detect the high correlation pairs? Let's see. I do already see that the correlation number between wealth and home value is 0.7. That's expected. Well, check out this 0.95, and that is the correlation between wealth and income. Okay. Oh, we have also a correlation between income and home value. And then we do have 0.75 here, and that is the correlation between education and home value. Well, that's what the data tells us. It's okay, we are going to go ahead and use all these sets of information as independent variables, try to predict the balance. But you're going to see that VF values of these, some of these independent variables at the end is going to raise a red flag so that I have to do something about it, okay? All right, let's go back and let's start building our multiple linear regression. All right, I will close this graph. You can export it, save it as an image or as a PDF, wherever you want. It's a nice looking, you know, correlation analysis. Let's, as I said, by using the banking data, let's create our linear regression model 5. So this is the name that I just gave. You can name it anything else. And remember, LM function is the one that we use to put together linear models, in this case, multiple linear regression. And then this tilde is just to represent the fact that we would like to represent balance as a function of all these 5 independent variables. All right, let's run this. And the summary LM5 should give us the results. Okay, so what do we see here? We do see that these are the residuals. We're going to take a look at the plot of this linear regression. What the first thing that we do is to check the significance of regression. We do see that this p-value is very low. It's very small, almost 0, and that's less than our level of significance, which is 0.05. And it is telling us that there is at least one independent variable that is explaining the changes in the dependent variable. And what are those dependent variables? Before I explain that, let me take a look at the R-square value. Basically, it tells me that this multiple linear regression is explaining 94, almost 95% variation in the balance. So this is a really good number. I mean, we can explain the 95% of the variation in balance by using this. It means that I could use this to predict, to locate actually where to open up my next branch. And then adjusted R-square value, as I said, this is different because R-square value is adjusted based on the number of the independent variables that we keep in the model, okay? So let's see which independent variables are significant here. So obviously, wealth, these 3 stars are telling me that I do have a very small p-value, so that's good. This one is also a small p-value that's less than 0.05. But check out education and check out home wealth, right? So those p-values, although this is slightly above 0.05, it is still above 0.05. You can make a executive decision here. You can maybe select to keep this education in your equation, but I'm not going to do that at this point. I'm going to consider it as an alternative to get rid of. I do have 2 alternatives here. I do have 2 independent variables. Education has a p-value of 0.05, and home value has a p-value of 0.4. Well, obviously this is larger. What I will do is on my next multiple linear regression model, that's what our modeling approach and philosophy was, to drop the home value from the equation and rerun the multiple regression. All right, let's do it. Before I do it, let's check the regression assumptions to see whether we satisfy them, okay? So we already created regression model 5, and we're going to plot the regression plots. It says hit next. Oh, you have to come here, click on console and hit enter. This is the residual plot. And then as you can see, this red line is almost smooth. So linearity is satisfied. And also you see that those circles are randomly scattered on this chart. They're not showing any pattern. So homoscedasticity is checked. Constant variance, it basically tells me that whatever my set of independent variables are at any level, I still get a constant variance. I might have some outliers here, but majority of my points here are on this line. So I'm going to treat that my residuals are normally distributed. This is again a weak assumption. But yeah, so I would assume that those residuals are normally distributed. There's one more plot, actually 2 more. So this is the standardized residuals to see if there is any outliers. As I said, the rule of thumb is to look for standardized residuals in square root to see if there's any above 3 or -3. I don't see those, although observation 85, observation 91, that's what it is giving me the indices in this data set. If you are into see like, what these, data points are. So you can definitely look further. So you can locate observation 91. Let's see if we can find it. All right, so let's see what is 95 telling us. So 95 telling us that, so our average age in this neighborhood is 33.9. Education average is 12.1. And our income level is 32,813. And what is wrong here, or what makes this as an outlier? I believe compared to others, this is showing me a high balance based on this information. All right, it might be the case, or it might be a data collection error. It might be something else, but this is the way that you can see if you made any mistake during the data collection part or not. And then the next one, let's see, enter one more time. Again, this is the Cook's distance to see if there's an outlier here, but you already know how to detect them from the previous plot, so I'm not going to spend too much time. So we can conclude that our assumptions are validated here. We could safely use multiple linear regression. We already analyzed p-values. As I said, we are going to drop the home value, right? Because education p-value was also greater than 0.05, but home value had the highest p-value. So we dropped it. All I did is I copied this equation, but I did not include home value into the right of it. And let's run this. And let's run the summary to see the results. Regression p-value is a check. Our multiple R-squared value decreased. This is expected, but not really that much. It was 95. Well, let's see. The previous lead was 94.69, and now it is 94.65. As you can see, dropping home value didn't really, create too much, decrease in the R-squared value. And this is good because we got rid of a noise. You don't have to really look into home value, but everything else, right? At this point, that's a good thing. I mean, dealing with less data is always good. And adjusted R-squared value didn't really decrease that much. So this is cool. And check out my individual p-values. They are all significant. So I can set up my equation by using age, education, income, and wealth. And I can use these estimate coefficients here, right? Are we done? No, we are not done. We should take into the VIF function. And we have values of these individual independent variables. There might be still a multicollinearity issue going on here. I suspect that it is going to be between income and wealth because those are very, we already saw that those are correlated to each other, but there might be a multicollinearity issue between these two. All right, so to calculate multicollinearity, unfortunately, we have to install a new, library. And it's called car package, okay? If you haven't installed it, make sure that you run this 64 line, install that packages in parentheses car, hit command return or control enter. I already installed it. I'm not going to install it one more time. And after you install it, make sure that you add a hashtag here to make it as a comment. And then after you do install it, you have to call this, you have to load this library, loaded it. And you just need to call VIF and in parentheses, the name of the last multiple linear regression model. And that was LM6. And that's simple. You don't have to really deal with the ugly math equations. And if you do it that way, let's check the VIF value. So these are the VIF values. So H has a VIF value around 1.3, that's good. 1.6 is good. Well, check out these two. As we suspected, their VIF values are greater than 10. Well, which one has the highest VIF value? Obviously income. So what we do is we drop income, okay? And let's see what happens. So we create another regression model, LM7. This time it is going to be only including age, education, and wealth. We drop income. And let's run this. Let's run the summary. Well, my R-squared value got down by 1%, and that's okay because income was having correlation with wealth. And guess what? I mean, with 93% R-square value, we could still explain a lot in balance by only using less data, and that's a good thing. And then all other p-values are significant, right? So we can call one more time to see if there's any VIF issues. Well, you see that all the VIF values are around 1. And here we stop. Our ultimate linear regression equation can be declared as balance in terms of intercept, age, education, and wealth. Okay.